Hello, everybody. Hello, and welcome to the July webinar presented by the Underground Construction Association Young Members Group. My name is Tony Bauer, and I am one of 3 members of the UCA of SME Standing Committee for the UCA Young Members. I'm the founding chair, and I'm joined by Aaron Clark, the Professional Development Chair, Shannon Goff, the University Outreach Chair. As always, please join us for our webinar series on the last Wednesday of each month. Next month, on August 26th at 3 p.m. Eastern, Nasri Munfa and Senior Vice President at HNTB and Wojciech Gall, Principal at Gall Zeidler Consultants, will present on the Eurasia Tunnel as part of the Istanbul Strait Road Tube Crossing in Istanbul, Turkey. As always, you can register for next month's webinar at the events page on our website. Today, we continue the webinar series with a presentation by Paul Madsen on tunnel engineering, challenges and opportunities on the Devil's Slide project in Pacifica, California. Paul received his bachelor's in civil and construction engineering from the Engineering College of Copenhagen and a Master of Science in Geotechnical Engineering from Heriot-Watt University in Scotland. He has also completed the Tunneling Soft Ground course at City University in London, England. Paul has over 25 years of experience as an engineer, superintendent, and manager for estimating, planning, and executing EPBM and NATM tunnels in soft ground and rock throughout North America for Kiewit. Paul was responsible for estimating the Devil's Slide tunnel excavation and transferred to the project as the Senior SEM Engineer and later as tunnel manager during construction. He was responsible for the safety and quality of all tunnel construction, daily interpretation of instrumentation, and assessment of adequacy of ground support. Paul, thank you very much for presenting to us today, and when you're ready, you can please share your screen.
All right. Here we go. So now all of you should see a beautiful slide of the Pacific Coast Highway. I'm very happy to be here and have this opportunity to talk to the future of our industry here today. And I have found out, however, there are some people who are over the legal age for attending a Young Engineers WebEx. So I'm also talking to the past of the industry, which is just a great privilege. So I hope you're all having a good hump day here. Wednesday, it's all downhill from here. So just a few things before we get started here this afternoon. Typically, I like my presentations to be more than an interactive process, which is a bit difficult using this type of WebEx. So what we're going to try and do here today is that I'll stop along the way through this PowerPoint presentation and we'll take some questions. I believe this thing is set up so that you guys can type in some questions along the way as we go. And we have Jackie with us here also, who's going to help get these questions up on the screen so I can see them. So as I mentioned, we'll try and stop along the way so that any questions that you may have along the way, type them up as they come to your mind and don't wait till the very end, because if we wait till the very end, well, you might have forgotten the question or you're all eager to get on with life and we won't get to talk about them. So just want to point that out. I'm counting on you guys' anticipation in this thing. So if there's some locations where you have several people in a room right now, you should probably dedicate one person who's going to be the person who's going to type the questions so that we're all set and ready to go. I don't know if there are any questions to that. You can write that up on the screen now and we'll get that in. Otherwise, just want to briefly tell you how I got into tunneling, how I was so fortunate. And it was more or less by accident, which is what happens with most good things in life. And got in on a project back home in Denmark, a very challenging project. And for me, that was I think a very, very fortunate thing that happened there. I got in on a project where over the couple of years I was there, we went through a lot of technical and operational challenges that really made the foundations for my future career. And as we get to the end of this presentation, that's something I'd like just to emphasize a little bit more on how important I think it is for young engineers to get involved very early on in their career, because it's gonna shape who you become in the future. So my experience has always been on the contractor side, and I've been fortunate to be involved with some design as well on some of our design build projects, and carry the project from its infancy of conception all the way through to completion, which is it's a great experience to be able to have. There's really so many things to learn that whether you work on it as a contractor, if you work as an engineer or supplier on the equipment side, this business that we're in is so challenging and full of opportunities that you can make a whole career out of it. So up to this point, I think there are any questions at this point. Are there, Jackie? I also want to make sure that Jackie is with us.
I am with you, and Paul, there are no questions yet. But we have invited all of our participants to use the chat panel to send me the questions, and then I can read them back to you.
Thank you very much, Jackie, and good to know that you're there, helping me out when things go astray. So today I'd like to talk about this. Really is a baby of mine, the Devil Slide Tunnel. And those of you who are joining us from the Bay Area, you should definitely know this project. So as we go through this presentation, I'd just like to say that it's going to serve like a dual purpose. As we go through, we'll talk about the specific tunneling method here. So there will be a little bit of an introduction into the tunnel methodology that was used in this project. But I'm also going to try to talk a bit about what duties our young engineers had on this project and how they were able to grow on a project like this, and some of the areas of work where they got involved. So it's going to serve a dual purpose as we go through here. So let's just get started here right away then. So this is our construction site, or was our construction site on the Devil Slide project, and it's a beautiful location there in California. The south portal of the project is what we see here. And here's just some facts, and I'm not going to dwell on these too much, but what I want to point out here on this slide is just the purpose of this project. The purpose of the project was to bypass this section of Highway 1. Looks a little bit similar to the previous slide, but it's just north of the previous location, right where the road runs along the steep edge there and the cliffs. And this is where the Highway 1 occasionally over the years have slid into the ocean. And that was the purpose of this project, was to bypass this section that we're looking at right here. Another thing maybe to point out was the amount of shotcrete shot on this project here with 50,000 cubic yards of fiber reinforced shotcrete. There's a large amount, and I think it's one projects in North America with the most amount of shotcrete on it. So this is, I know this is a bit of a tacky old slide, but it does serve the purpose of pointing out the features of the project, if you will. The alignment of the tunnel, as you can see, is a straight line. It's two bores, 30-foot diameter each, with 10 cross passages along the way, and it runs from the upper left-hand side of the slide and down to the lower right-hand side where the south portal is located. And part of our project was also this operations and maintenance center, which is located a little south of the project. Now here, one of my pet peeves, I'll start with that, which was geology on the job. This project ran through 3 major formations, a granite diorite, sandstone, and then a siltstone in the north end. And as an engineer on this, when we first start looking at this is what you start digging your teeth into here to understand as much as you can of the geology and that's available to you anyway. And you can see we have some interesting features on this project here. We have, start looking at it, you have a relatively high overburden for North America, I should say. If you're mining in the Alps, this is nothing, but for us here to have 1,000 feet of rock over us. It's quite a bit. We see there are some fault zones between the main geological features, which could create some challenging to excavating the tunnel. The north block there was completely jointed and fractured, almost soil-like conditions, whereas in the central block we had some very hard rock. And another interesting thing here, if you look at it from a hydrological standpoint, if you see that blue line, or see the blue lines, the water tables, how they're staggered across the alignment, and you see how when we mine from the south going to the north, we will go through a fault zone where there will be an instantaneous increase in the waterhead. Things like that are things you want to look at early on in the process to identify potential challenges and technical issues that you're going to deal with once you get out and build the job. You need to properly address that in the estimate for the project. You can imagine there, for the water table to make a jump like that, that would mean that red hatched area there in the middle is impermeable, right? And for it to become impermeable, that means you have to have some impermeable material, which would be like a clay filling. And to get clay filling in a material like this means that the thing must really have moved and got moved around a bit to create that clay filling, which really is a challenge to your excavation once you have to mine through it. So this is where it all starts in the early process on the project and the estimating phases to understand this the best way, and that goes for everybody in the project, whether you're the young engineer or you are the experienced tunnel superintendent.
Paul, we do have a question. It says, it seems like this is a very rural location. What challenges did that provide?
Actually, it looks like it's very rural, but it's just outside of San Francisco.
Oh, okay.
Yeah. So it's on the Pacific Coast Highway between Pacifica and Half Moon Bay. So I know the pictures, they look like it could be miles and miles away, but we were only 8 minutes away from the nearest brewery, so it was actually a very good location.
It sounds like it is. Yes. Thank you.
You're welcome. So yeah. So just on that one. Our craft and all our craft came from San Francisco and north of San Francisco. So we didn't have any problems with staffing the job from a craft standpoint at all. Yeah. People were just living around the area. Now the way we excavated and supported this tunnel was by the use of sequential excavation method. Press the right button here, and that it's a way or tunneling approach that has many names around the world. You'll hear it being called the New Austrian tunneling method, mostly in Europe, especially in Central Europe, continental Europe. SEM, that's what we call it here in North America. Sprayed concrete lining, that's what the Brits typically call it. And then there's several other names that you will see it referred as when you read literature from around the world. One I personally like the best is really the observational method, and we'll get right into that here. But for the purpose of the presentation, I'll call it SEM. The reason why I like the observational method is the SEM process, if you will, is all predicated on the ground support is selected to work with different ground conditions, if you will. You're taking advantage of the strength of the ground that you're excavating through to support itself. Many of you will have probably seen the pictures from the old tunnels or movies from old tunnels where you see big heavy timber and steel support that were designed to carry a big, like half a mountain above it. In those days, the engineers really designed that support to carry the dead weight of the rock above the tunnel. But the SEM is a lot more economical, because what we do in that process, we just help the ground support itself, if you will. The ground has a tremendous strength, especially good rock, of course. You can create a hole in it, and the hole will stand up, in some cases forever, without any kind of ground support. And then that's what this slide here illustrates. The top arrow there shows that if we have good ground conditions to the left on the slide here, we need minimal ground support. We can get away with just putting in maybe a little bit of shotcrete and a few spot bolts. But then as the rock mass changes and it becomes more jointed or weaker rock, we have to augment, if you will, the bearing capacity or the strength of the rock itself to carry itself. And then once we get to maybe a soft ground condition to the right-hand side of the slide here, now we have to create a whole closed ring to support itself with possibly some heavy pre-support. So we adapt, or we observe the ground and we adapt to the ground condition as we go along, and that way that ground support becomes very economical because it's really designed on the spot or implemented right on the spot. So of course the designer ahead of time have to come up with some ground support classes for the different type of ground along the alignment. And on the Devil Slide project we had 5 major ground support types, and I'm not going to get into any details on these. I just want to show you guys what a typical tunnel ground support looks like. Here this is for the good rock. You can see the tunnel has a flat bottom. We're not relying on any kind of ring closure. It's got fiber reinforced shotcrete, just 100 millimeters, and then some rock dowels. And then as we go through these categories, see how we get more stuff showing up on these drawings. You know, it gets completely crazy here when we get to category 5, which is what we used actually in the north end of the job in the normal soil-like conditions. Here you have a closed invert, you have a closed ring, you have 300 millimeters of shotcrete, all kinds of bolts and spiles and canopy pipes and face mount. You'll also notice that the excavation round length is here just only 1 meter per round. But you know, this thing here starts all the way in the estimating stage, and we will sit with a whole group of us, including many young engineers, and we'll have to analyze these different ground support types and take off the quantities. So if you're a young engineer with a contractor and you're in the office, this could be one of the things that you get confronted with, that you get this slapped on your table going, and somebody goes, here, now I want you to take off all these quantities here. So you have to take off the different type of rock bolts, the shotcrete, the excavation volumes for the different excavation lifts for each round, so that you later on can do analysis of cycle analysis for the excavation.
We do have a question, Paul.
Yeah, Jackie?
Have you ever thought, instead of SCL observation method, etc., to use a TBM for the excavation?
Yeah. No, we didn't consider it for this project here because the project came out on the street to be excavated as an SEM tunnel. You could analyze it and see if it economically would make sense to make it a TBM. But there are certain reasons why you pick an SEM excavation or use SEM over a TBM. Some of those, I don't know if you call them advantages or disadvantages really, but some of the differences would be to use a TBM, to mobilize a TBM, you really want a certain length of tunnel. And this tunnel here was 4,000 feet long, or 2 times 4,000 feet. So you want to make sure that you can, if you're buying a TBM for this job and you're writing it off over this length of this tunnel, you want to make sure that it financially makes sense. A couple of other things, the geometry of the tunnel, the size of the tunnel. It will have to be a very large TBM, or nowadays you can get TBM much larger diameter than this, but it is a relatively large size for a TBM. And then lastly on this project here, I would say it was the varying ground conditions along the way. it would be more difficult to find a TBM that could handle all the different types of rock that we encountered along this alignment. Whereas, as I mentioned, the SEM approach, you can adjust or adapt your ground support to the actual ground type. But it is of course a lot slower process than using a TBM. I think that answered it, Jackie.
I believe so.
Yeah.
Thank you.
So now that we've got the job and we're out there building it and everybody is excited and we have to select what ground type to use, this here looks like a crazy octopus, but it's how do we decide what ground support type to put in? Well, we gather information through doing probe drilling, collecting groundwater data, mapping the rock, everything that we see in this here MPBX, that's multiple point borehole extensometers. So here our engineering staff will get involved in collecting all this. We will have engineers collecting information from probe drilling. We'll do the laser scanning, which was a new technology there at the time when we did this project. And once we gather all this information, the convergence survey, we will have engineers analyzing the convergence, so the deformation of the tunnel, how much the tunnel will deform, and then put it all together in a big pot and make a decision of what type of ground support do we need to implement for our next couple of rounds. We would meet with the owner on a daily basis and go over our observations and make sure that they were on board with the decisions that we were making. It's an interactive process on a project like this. It's not something you sit and go and do in a room by yourself. A lot of people takes part in collecting and analyzing this data on a daily basis, and that's not something you can learn in school. You know, I feel really happy for the young guys who were out there that I was working with on this project, who were able to get exposed to this process and see it and be part of it, because it's a huge resume builder for your future career if you have an opportunity like this to be involved with it.
We have a question.
Yeah.
Did you grout any zones to limit the groundwater inflow?
No, we didn't grout. But what we actually did was we drilled out ahead, and we came up with to drain or lower the hydrostatic head to eliminate any issues with mining right into that high water pressure we saw there when we went from one formation to the next. So together with the Caltrans and the construction manager on the project, we agreed to do a several long horizontal holes from the north end of the tunnel, where we drilled through these formations and we lowered the hydrostatic head. So when we got to these formations, we had drained the water, and frankly we never had any issues with any kind of groundwater inflows, apart from minor inflows along the tunnel while we excavated it. So so grouting wasn't necessary. It could have been used, but it ended not having to be used. And this flow chart here is not something you all have to remember, but it just shows this whole process on how the information feeds back into itself, and you use the information that you learn along the excavation to adjust and make the support better. And now here's some more exciting pictures. Now we looked enough on all that the text slides, so let's look at some. This is more the meat and potatoes of the game right here. This is one of our big AM105 roadheaders. That's what we use to excavate most of our tunnel with. It's a 125 metric ton beast from Austria. And the field engineers who worked in the headings, I think they're probably the ones that had the coolest job on the project. They would get to ride shotgun on this thing here, and their duties included the guidance system, working with the guidance system for the machine here. So the machine has a guidance system that you use so that you can control your excavation profile. They'll be part of course, mapping the geology as we were tunneling through it, and doing checks on setting the lattice girders. We can see the lattice girders there, that they're exposed until the second pass of shotcrete gets applied. So they were intimately involved with all steps of the operations, and they worked very closely with the heading crew. The heading crew depended on those guys, and it's great to witness, and it was great to witness the guys get the experience that they did on this project here. We had areas where drill and shoot as well. So here we're mucking out the shot rock with a track loader into one of our haul trucks. So here you get exposed to having to handle explosives and all the permitting and everything that goes with that. So I said the guys there, they got the same experience as you normally would get on 3 different jobs on just one job on this one here. And how much they wanted to learn, it was really just up to themselves. This is installing some of the pre-support drill jumbos here. And you see the picture, on these pictures, a lot of equipment. So other engineering duties on this project here, if I could start rattling them off, a long list. We had equipment engineers in charge of tracking the equipment hours and the maintenance of the equipment, and the millions of dollars of spare parts that we were dealing with on the project for all this specialized equipment. We had electrical engineers, and then show you some more stuff as we go through here. But the excavation is sort of the sexy part. I'll just go back to this slide. It's a little cooler than the other one. That's sort of what I like the most. But there's a lot of work that comes after that on a project like this. Once the initial shotcrete liner is in, the excavation is done. Now, all this other work that many of us tend to forget about comes afterwards. These are all the components of the final lining that gets installed in this tunnel once it's excavated. If we start from the bottom there, you can see these abutments down in the bottom. Those are the foundations for the arch. We have walkways, and we also have the whole final arch structure with all the different conduits and embedded boxes and whatnot. Walkways with conduits in it, precast roadway drainage. And to install all of this is very engineering intensive. We have engineers involved with all the different phases of this work. Last one I'll talk about later, you see the metal panels. It says the metal panels there. That was a big learning experience. It's an architectural feature that we had to install, and something that we typically don't deal with very much. So, and Jackie, you just interrupt me if there are any questions that pops up.
I was just about to do so.
Okay.
The question is, did you compare any data from the monitoring, for example, the indications of the pressure cells, with the results that came from the numerical analyses? If yes, how close were they? I can read that again.
No, I got it. Okay. I got it. I would say that it's a little bit out of my wheelhouse when it comes to the analysis part of it. I can talk to it from just the tunneling standpoint. I'll say the pressure cells, it's hard for me not to sort of sound rude when I talk about the pressure cells, but I've had so many, I should say, disappointing experiences with pressure cells. So it's sort of funny somebody asked that question, because the pressure cells are installed in the shotcrete lining, and the purpose of them is to take the pressure from the ground onto the shotcrete lining and also monitor the pressures or the pressure inside the shotcrete lining. And I'm not a designer, but from a hands-on standpoint, when I'm out there in the tunnel and I have to install pressure cells, and most of the time as engineers, they would like these pressure cells to be installed in areas of high loading on the lighting to understand what the loading is, and in areas of poor ground conditions. So you're out there and you want to install these cells on the worst rock you can imagine, or the worst ground you can imagine along the alignment. And it starts to me to turn into a bit of a safety hazard getting these things in. And I've talked to engineers about it in the past, and they said, well, why don't you just shoot your initial shotcrete lining and leave a window and then put the pressure cells in? I said, yeah, I can do that, but what happens with the shotcrete that I put in to encapsulate the pressure cells when I do them later on? Well, that shotcrete is a lot younger now than the shotcrete that was already installed. So if I'm the rock and I'm loading this initial shotcrete lining, I'm going to go to the stiffest and strongest lining first. I'm going to go to the shotcrete that was initially installed. And that's where the loading is going to go, because the young shotcrete that was installed around the pressure cells is never going to see any of that. So that was a little bit of a, I know, a bit of a preaching on the pressure cells. But what we did do, and our most important monitoring on this project here, was the convergence readings. So the engineers did take all our convergence data, and they took that and they related it back to what the convergence and what deformations they had seen when they did the design. And as far as I know, again, it was not something I did, but as far as I know, I believe that the convergence that we observed were in line with what the design analysis had indicated. So I think that answers that question. One thing, just to get out on the table with this convergence reading, and to remember, if there are people here on the call who are working with this and defining convergence limits, I think it's something you have to be very careful about. That if you have a computer model that shows you a certain amount of deformation of the tunnel, and now you're going to turn that into a contract document for a designer, or sorry, a contractor to go and bid on, you need to be realistic and upfront with what those numbers are, and not go out and say, yeah, okay, my analysis showed me I could expect 4 inches, but I want the contractor to react, so I'm going to just tell him it can only move 1 inch. Because what's going to happen is, if your model is halfway right there, or a little less than halfway right, and you get the deformations, then everybody gets up in a tizzy over something that may not be a big issue at all, because it actually matches what your analysis show. I also know a little bit of a long-winded answer to that. I hope that's okay.
Yes, sir.
So, okay, so that's, we also want to make sure that we don't end up spending the whole afternoon here. So then we just go through some of the final lining work here, or the steps of the operations in the final lining with placing abutments. And here we see the abutments. We also see a closed invert section. So this is in a category 5, where we closed the final lining in the bottom and created a full ring. This is our formwork for that, also nicknamed the Millennium Falcon. This is the waterproofing, which was installed by a subcontractor. So all these steps are very engineering intensive, and they actually took place while we were also excavating, which made a big challenge. So we had a huge staff here at this point in time where this work was going on in the process, because we had guys working on excavation on 3 shifts, engineers on that. We had our surveyors, our equipment engineers, electrical engineers. We had guys planning upcoming finishing work, and we had guys involved with the concrete operation and monitoring the subcontractors for the waterproofing, and as we'll see here in a minute, the rebar installation as well. These are the rebar gantries from which we installed the rebar in the tunnel being assembled, and they were, you can imagine the engineering that goes into planning, sizing, and of this type, and procuring as well this type of equipment, all done by engineers, and many of them had never seen or heard about this type of work before. Rebar itself was a big deal in the project. Rebar sub here. 2 layers of rebar. And here we see all that spaghetti rebar. We also see all the components of the final lining here. Really, you start from the top with all the rebar. See all the lights there. You're wondering what in the world do we need all those lights for? Well, that was because the inside of the tunnel was stained black. So when the tunnel is stained black, to get the amount of lumens you need for illumination inside the tunnel, you need a bunch of lights, and that's what you see there. You see the safety walk, or safety shake, it was called, at the lower part of the arch. This was a form liner that was installed on our arch form, which was the first time we ever done that. I think it was the first time anybody had ever done a thing like that. And it was stained yellowish. We see the walkway with all the conduits and the precast drain there for the roadway that is to go in later on. All these multiple steps. It was fun to build anyway. Here the formworks, they're built over in Switzerland. So here's where your planning has to get way out ahead of the operation to ensure that you have enough time to engineer, procure, build, ship, assemble all this formwork here. I think the picture on the left there, that's a load test of the stairs. And here's the form liner that was installed on the outside of the forms to give that texture. And as I mentioned, we were excavating further up the tunnel while all this concrete work was going on. Further back in the tunnel up front, we were still excavating, and we had to park all our equipment and all our stuff up front. So a lot of effort going into keeping track of all the gear and where to park it. And talking about engineering duties, if you see those 2 ducts running along the tunnel here, the ventilation of this project in itself was a huge deal. And a lot of people learned a lot, whether they wanted to or not, about ventilation schemes and dust collecting and along this project, because as you can imagine, when we're closing the final lining further back in the tunnel, we can't have these ducts hanging up there, so we had to come up with some alternative schemes to that. And one of them is right here. We actually sucked air in through one tunnel, ran through a cross passage with some of the ventilation system, and then blew it back out the other tunnel. And that's what we see here. So all the engineering of this duct works and everything that goes into it was fun. And here again, just to emphasize the logistical challenges of excavating and concreting on the same project. See, they're trying not to impair each other too much. We have the haul truck on the upper right-hand side, the haul truck running in and out of the tunnel while a crew is trying to place abutments at the same time. One of the haul trucks actually is backed into a cross passage, as you can see there, just to get out of the way, because we need to haul the muck as fast as we can, so excavate as fast as we can. The excavation was, of course, in the critical path here. The lower right-hand side of the slide there is the abutment installation, and this is just one of the smaller little operations along this whole process. And many of the guys on the project, of the engineers, were able to start out on the project working maybe as a heading engineer, or maybe even earlier as planning for the shotcrete, for example. There was one guy just solely dedicated to that early on, and then transferred into be a heading engineer, and then to maybe transfer down to do some work in the office or plan for a concrete operation, and then actually go out in the field and execute the concrete operation. And we made some of these guys like a foreman or superintendent for that operation, so they got some hands-on experience with running the crews and supervising crews, and they were responsible for the safety of the crews and really a great opportunity on a project like this, something that everybody should take advantage of if they get on a project like this. And now we're getting close to the end, and I just want to show some of these more fancy pictures from the project. This is the North Portal, and this is textured concrete at the North Portal. So this concrete here was cast with a form liner, and the texture on this form liner here had to match the texture of some existing rock out on the project. So a couple of engineers were tasked with the task of taking these imprints of the existing rock. However, in some cases that rock, the only place it was found was on a nude beach adjacent to the project. So I think many of us were just happy when we finally saw this here being built, that there weren't any suspect imprints anywhere on the portal structure that we had to chip out later on. And then it was all hand painted, you can see here. So it's a beautiful piece of work if you go out and see it. I hope Caltrans is taking well care of it out there. And this beautiful slide here is what the final tunnel looks like. You can see this is a different texture right here on both sides of the tunnel with a roadway in, and here these metal panels I mentioned earlier, which ended up to be a real success story because they're not used much in North America, and we couldn't find anybody who really had the expertise to do this work. So we identified that early on, and we had some of the young engineers. Again, it didn't matter if you were young or you were old or experienced or inexperienced, because nobody had ever seen it before. But we got into it very early on and did a lot of research. Got our foremen and superintendents or structural guys or carpenters involved and looked at the systems for installing these and planned it down to the nth degree really. And when we went out and executed it, we executed it without any safety incidents, perfect quality, and made a pretty penny on it as well. So that was a real success story right there. So by now you should know a few basics about SEM tunneling, and you'll have an idea about what to expect as a young engineer on an SEM project like this. And Jackie, before I wrap up, are there any questions here right now?
No, sir. There are no pending questions.
Okay, the crowd is probably asleep. So it was really a great career builder for many young engineers. And to wrap up for those of you young guys on the call here, I'd like to leave you with one piece of information, and that is, from my years of experience in this business and counting myself in as a young engineer, your future success, your fame and fortune in this great industry is really directly proportional to the amount of sacrifices you're willing to do early on in your career. And by sacrifice, I don't mean like chopping off your left hand or anything like that, but the amount of effort you put into getting involved on the project and learning is what's gonna be.
And we do have a couple of questions have just come in. Could you address how much more this tunnel costs per foot than any other tunnel you have built?
Actually, I've built tunnels that are a lot more expensive than this one. And to that, so it's not that much more expensive than this job ended up in a $400 million range for a total of over 8,000 feet of tunnel with 10 cross passages, roadway, architectural, and everything else. And people can do the math on that one. And at the same token, we built a tunnel in New York that was that close to 100 million for 100 feet, so 105 feet. So it can be all over the place. I don't think this is particularly expensive. I think maybe the cost per foot in North America for this type of tunnel, if you start comparing it with tunnels in Europe, is higher, but that's a lot of other things contribute to that. So, any other things, Jack?
Another question, did you consider a spray-on waterproof liner?
We didn't on this project here. It was specified with a PVC membrane. I don't think I would have preferred it. I don't think I would have wanted to do a spray-on this job. There's several reasons for that, Jackie, and one of that is that it's a fairly unknown system. What I have learned from that with that system later on from projects around the world, I don't think it would have been very well suited for this project. I think the spray-on waterproofing, it works good in areas where there's no water, and I know that sounds a bit silly, but that is the fact. The surface preparation we would have had to do on this job to make spray-on waterproofing economical, it would have been more expensive to do than the PVC membrane. And then lastly, a spray-on waterproofing would have obstructed the tunnel and would not have enabled us to perform multiple operations in the tunnel at the same time, because the dust from the spray-on would have gone up and reached up to our heading engine or our heading crews. With the PVC membrane, we didn't have that issue at all. The PVC installation could take place while we were doing all our other operations at the same time.
Okay, the next question, do you see the tunneling field growing, shrinking, or staying the same? What do you think is the outlook?
If I look at a worldwide view on it, it's definitely grown. It's grown tremendously over the years that I've been in a business. I think here in the U.S. We're a little bit behind actually on what, if you look at the growth around the world, especially in centers like London and the Alp regions. You look in Australia and New Zealand, the amount of tunnel work that's going on there compared to what we have in the U.S. So there's a tremendous amount of work out there and a tremendous amount of opportunity. I wish, or I think that the industry will keep growing here in the U.S. It almost have to, if you look at the infrastructure development that will have to take place over the years. It's just, I think our political system are completely way behind on realizing that. But to answer the question simply, I think there's a lot of work coming up and will be in the future.
Okay. Next question. Did you experience any face instability issue? If so, what were the effective measures used to control the face stability?
Oh yeah, we had several instances of that, and it's always interesting when you have to deal with that when you're going through some poor conditions. And my preferred method when you get into ground like this in this type of tunnel is I like to implement the face mount. You have a choice. You could go with a face mount, which really leaves a pile of, or you leave some ground on the center of the face that prevents the face from moving on you. I prefer that compared to face dowels, because if you are getting into like a soil-like condition, then the amount of face dowels that you have to put into to get the same effect as the face mount is the face mount is basically it's cheaper and faster to install. Sometimes we would combine the two. We would have a face mount and we would throw in some face bolts as well just to support that. And then of course having an adequate pre-support, whether it be spiling or canopy pipes, that's of course important.
We have another question. What do you believe are the major safety concerns on this project?
The major safety concerns on this project, and I think not just on this project, and on many similar or many tunnel projects, is stored energy, and we did not have anybody get killed on this project, thank God. But stored energy in air lines, in slick lines, stored energy is also rock or shotcrete overhead. I think those are the biggest risks I would say for safety on a project like this. If I had to put number one, yeah, I would probably go with pressurized shotcrete lines, or freshly applied overhead shotcrete is also as a close second to that.
Thank you, Paul. We have two people who have asked you, were there any key lessons learned from the project which you could share with us?
I think I just rattled off many key, but if I had to go for this to go smoother, the key lesson, I think it's something that's already known to everybody, but I think it's a key important for this kind of project to go well. It's really the close technical, to work closely between the contractor and the owner on a technical level on a day-to-day basis. We had so many benefits from being able to separate like the contractual and economical issues from the technical, and both the owner and us really gain from that. When we built the job, us who were out building the job could do so keeping the best solution in mind at all times and not being sort of polluted, if you will, by contractual issues. We had a team of people, both on the owner and on our side, who helped that. And the upper management on both sides were interested in that we built the tunnel the safest, most economical way. And we were able to do so because the way we had structured the organization. I think that's probably the biggest key to making a job like this a success.
Another question, did you install any of the umbrella pre-support system? If yes, how was the installation difficult?
No, we had it's a canopy pipes or umbrella pipes or canopy pipes or whatever we call them. Yeah, we did install quite a few of them, and we were fortunate because we had experience with them. We had experience with them from a job back in 2004 out of Dulles Airport, where we installed them the first time. Then we did a test program where the tunnel superintendent on this job and myself had been up at Colorado School of Mines doing a little test section with canopy pipes. So we sort of knew what we were getting into, and we actually, I was not going to say we had a great, yeah, well, I would say we had a great time putting them in, and we didn't have any challenges that we didn't know of with them. Really, we identified that the alignment is key. Setting up the jumbo is key to making sure the pipes get straight. Grouting them was a key, that you do a proper QC on grouting the pipes up and ensure that they are all grouted, especially when you're on a rock where the grout communicates between the pipes. So I don't think we had anything with the canopy pipes where I can say that, oh man, that was a horrible experience or anything like that. They actually turned out pretty good.
Thank you. Another question is, why trucks over rail or conveyor for rock movement?
The trucks, one of the reasons for that was that our disposal site was on site. Back on the first slide, I'm not going to swap back there now, but our disposal site was just outside of the portal up a hillside. So we had to dump our material there. That was the only place we could dump it. So when we looked at conveyors, a couple of things with conveyors. The conveyors would interfere with the follow-on operation, the concrete operation. So if you imagine all these final lining steps with the waterproofing, the abutments, the arch concrete, all of that, you would have to bring a conveyor through that, which is fairly difficult. And frankly, we did look at it, and then the conveyor would then have to go all the way up this 24% incline up to the disposal site. And we had analyzed all these different steps and priced it out. And for that, we ended up ruling out the conveyor. The rail, a bit the same deal there. You imagine that we have areas where we have to place invert concrete. Now we have rail. The trucks were more flexible, a more flexible solution, and we didn't have to double handle any of the material. It went straight from the conveyor to the disposal site. So when we did a cost analysis on it, that was the cheapest way to go.
I think we have our last question, Paul, and it's a two-part question. Actually, it's not the last one. There's another coming in, but the two-part question reads, how many younger engineers were on this project altogether? And do opportunities to work on these major projects come around pretty often for a young engineer?
Or the number of engineers, you know, yes. I probably would have to guess. But if I look over the period when we built this job, and we had NTP in March of 2007, and excavation, you know, we were complete in 2011, so over 4 years. I would say that the amount, you know, we had engineers that went through this project who from the beginning till the end, we had engineers who worked for one part and then transferred onto other projects. And I would say that there have been somewhere, there must have been over 40 or 50 engineers or more engineers of, you know, all different positions, also in the scheduling and planning. Yeah, that's probably even low, Jackie. If it not even reaching, might even reach the 100 mark. It was a lot of engineers getting through on this one. Now when they come around, I wish I could say, yeah, these projects come around all the time. Unfortunately, they don't. It's a rare occasion that we see projects like this come around. So I think, and I know this is maybe not good if you're like trying to be a company man, but I think if I was a young engineer today, I would look at what projects are out there, and I would target where I would go and work based on the project more so than a company. And I know there are company people who would hate me from saying this, but that's how I would go about it, and that's what I did early on in my career. Also, when I was done with my first project, I didn't see if I was going to go and work for whatever contractor, A, B, C, or D, or engineer, whatever it was. I targeted some project and say, hey, well, I want to go and work on that project because that project is one that can give me a lot of experience. And I think that's actually a bit of how the future market is going to be. That's how it is elsewhere around the world, really, for young engineers. That there's not so much this culture of company people. I think it's probably dying out a little bit. If you want to build a resume, you need to almost target these projects and be prepared to jump around and say, okay, I want to go and build this project, whether it's as an engineer, whether it's or designer or contractor, and then try and target those projects and get on those projects to build your resume.
Excellent advice. Paul, we have used up our hour, and we do have a couple of other questions that I will relay to you through email later, and you can answer the people who asked the questions privately if that would be convenient for you. And if you could show, and you just have your very last slide, any questions that the audience may have, please contact Paul through the connections that he has here through his telephone or his email. I'm sure he'd be glad to answer any anything that you may think of later. We've really enjoyed your presentation, and this tunnel is beautiful. It's awesome. Paul, would you have any final words before we sign off? And then Tony, if you would have any final words as well?
Well, I will just wrap up, Jackie, and say thank you all for your attention and sitting in on this. Again, as I started out with saying here, whatever you guys put into it early on in your careers, specifically you young guys who are getting out there, your early dedication is going to pay back later on. There is no such thing as luck. You know, you'll find that 90% of what people call luck is really because of hard work. So if you get in early on some project and get into things, you'll later on in your career look back and say, man, I'm lucky. And that's all I really have, Jackie. Thanks again.
Thank you very much, Paul, again. And everybody, please join us next month when we talk about the Istanbul Strait Crossing project.
Thank you. That ends this session, and please double check the UCA website in another day or so. A link to this recording will be posted on the website. Thank you and good afternoon.